Okay, so hi everyone, I'm Akshara and I'll be picking up where Millie left off with the soils crash course. So you guys would have covered weeks 1 and 2, or you're about to cover week 2 material in your lectures, I believe. So I'm just going to cover week 3 and week 4. So this is where we kind of get introduced to stresses in soils, and how we can calculate things like the change in stress or the stress on a certain point in the soil at a certain depth. And then we'll also look a little bit at soil when there's a flow of water going through the sample, in which case you'll have to calculate things like pressure head, which we'll cover a little bit of in this crash course. So what I'm going to do is that I'll briefly go over some of the content. I'm sure that your lecturer will go through a lot of the formulas and everything in detail, and on the slides there'll be a lot of derivations and everything. So I'll just go through the questions step by step, and hopefully you can refer to your formula sheets and everything and kind of figure out how to work through some of the questions by yourself by the end of this. So to begin with, we'll just start with the week 3 material, which is all about using Mohr circle to calculate the stress transformations. So I'll just zoom into my notes here, because I think this is a pretty good place to start. So if you just imagine this diagram here is representative of a soil particle in a soil sample. At any point, there are 2 types of stress acting on that soil element, or the stress element. So one of them is the shear stress and the other is the normal stress. So I've highlighted them in green and brown there, so you can see where they'll be acting on the element. And the whole point of Mohr circle is that this stress element here can be orientated in an infinite number of directions, right? And for every different orientation, the value of the shear stress and the normal stress is going to change. You can use formulas called the stress transformation equations, which are here. I've written them down there, where they use the shear stress and the normal stress as well as the angle of rotation to determine the exact value of the normal stress and the shear stress at that point. However, as you can see, those formulas are really quite large and it'll be really time consuming to always have to use them, especially in your exam. So the whole point of Mohr circle is that you get to calculate these 2 values without having to use those formulas. So let's look at the diagram of the Mohr circle here. Your lecturer will go through the Mohr circle in a lot of detail, much more than I'll be able to. So I'll just give you a brief overview of each component. The middle of the Mohr circle here is your average stress, right? And then you've got your radius here, which is representative of the maximum shear stress value. And then on this side, the radius is representative, or it goes from the center to the minimum normal stress and then the maximum normal stress. These 2 points that I've circled in blue, they'll often be labeled like sigma 3 and sigma 1. Those are the principal stresses, and those are really important values because at those 2 points, the shear stress is going to be equal to 0, as you can see on the graph, right? So what is this diagram telling us? Basically, at any point on the Mohr circle, that's representative of an orientation. So as I said before, you can rotate the soil particle, the element that we looked at here. You can rotate this in an infinite number of ways, right? And so as you can see on the circle, there's an infinite number of points on this arc here, right? So, so there's an infinite number of points on this circle here for you to look at, and each point will have a different shear stress value and a normal stress value. So hopefully that diagram makes sense. There's a lot of like YouTube videos and stuff that you can watch to get your head around it. It's quite a difficult concept. I know I had to watch quite a few extra videos, but your lecturer will also have plenty of examples for you to go through together. So I think the best way to kind of understand it is by going through an example. And I really like this one here, because it gives you a really nice diagram to begin with, and then it shows you how to, or it guides you through drawing the actual Mohr circle diagram, right? So here, an element of soil is subjected to stresses as shown in this diagram. The value of the normal stress on one of the planes is just the sigma value here, so it's unknown. We don't know that value yet. But what we do know is that the stress applied to this side here, this plane, is equal to 30 kPa. And we also know that the shear stress on both planes is equal to 20 kPa, right? So as we go through this example, I'll kind of tell you a little bit about how to draw each section of the Mohr circle and what all of this means. So the first thing that we do with any Mohr circle question is that we look at our two planes. So we've got plane A over here, and then we've got plane B here. I didn't label them in the diagram. I should have. That's a good habit to have, just because it can get really confusing with more complicated questions. So here you notice we don't have a normal stress value for plane A, but what we do know is that the shear stress is equal to 20 kPa. One thing to always consider is the direction of the shear stress. If the direction of the shear stress is rotating the stress element in a clockwise direction, then the value is going to be negative. For plane B, we know that the shear stress value is pushing the stress element or rotating it in an anti-clockwise direction, and so the value for that shear stress is going to be positive, right? So that's how I've labeled those two planes there. Another thing to note is that the angle of rotation is 20 degrees. That's an important part that comes back later. But now I have enough information to draw the Mohr circle diagram, right? So in part A, it says, or it asks, what value of the normal stress must be applied if the major principal stress in the element is to be 100 kPa. So like I said before, the major principal stress is going to be this sigma 1 value here, and so we just label it as 100, right? So that's given to us in the question. That's the maximum amount of normal stress, and also at that point, the shear stress is going to be 0, right? And so we draw the Mohr circle assuming that that value, the maximum principal stress, is going to be 100 kPa, right? So by that logic, you can then go to your plane B, where you can see that the normal stress is 30 kPa, right? And so you can just kind of estimate where that falls on the normal stress axis, and I've just put it there, right? In this question, because we can assume that the maximum principal stress is 100, and also that the normal stress is given to us as 30 kPa on plane B, you can assume that the sigma value that is unknown is going to be greater than 30, right? Okay. So that's kind of how you draw it. This middle point here is going to be our average stress. It'll be labeled as sigma C, and that's a really important value when you're calculating your radius, which, like we said before, is going to equal your maximum shear stress value, right? Which is what is happening here. So that's the formula there. That's going to be on your lecture slides. And what we've done is that we've subbed in the shear stress value, which we know is 20 kPa, regardless of whether it's negative or positive. It's squared, and then you add it to the sigma x, which is just the normal stress plus the unknown value that we don't know, and it's like the average. And then you minus it from the normal stress at plane B, or like the sigma c value, right? So in this case, this is the equation that we get. So that's your first equation there. And then here is another formula that will be on your sheet, or it's just like a rearranged version of the one that we used before, where you've taken the maximum shear stress, which we know is 100 because they gave it to us in the question, and you know that that's equal to your sigma c value plus the r value, right? So in the end, after you sub in all of your values and work through all of the equations, you get a sigma value of 94.28 kPa, which you know is bigger than 30, so it means that your assumption was correct and it all works out, and your Mohr circle is pretty accurate, right? Okay, so let's look at part B, because you'll notice that in that first question, we didn't actually have to touch the angle of rotation, which I mentioned before was 20 degrees, right? And that's because in part B, they're asking what angle does the plane of the major principal stress make with the horizontal when the value is 100 kPa. So again, we're assuming that the sigma 1 value here is 100. We know that the 2 theta value, 2 theta is your angle on the Mohr circle, right? So regardless of what your angle of rotation is, represented on the Mohr circle, it's always going to be 2 times theta, right? So that's what's represented in the formula here. And you'll notice that we just used the tan inverse function to get a theta value of 15.94, which we can then compare to the horizontal diagram like I've done in this diagram, right? So the angle that we just found here, the 15.94, that's the angle between your major principal stress, so sigma 1, the plane that's, the stress value that's 100 kPa, and plane A. And then this line here, it's a little bit hard to see, but that is representative of the major principal stress, right? And then you've got your horizontal angle here. So that's kind of how, that's the value that the question is asking for. It's a bit difficult to understand when you haven't gone through the lectures yet, but basically what it's asking for is it's asking you to compare this plane to the horizontal, and it's asking for the angle that would be between the horizontal axis and then the element if the stress was at 100 kPa, which is what I've written down there. Okay, so that's kind of a very quick overview of Mohr circle. You'll notice that all of these formulas here that I've written in green, they're probably the more important ones for you to remember. I'm not so sure about your exam conditions, if the exam is still open book, but if it is, I would highly recommend just writing those ones down. They're quite important. So just a quick review. The most important parts of Mohr circle is that you've got your vertical axis representative of your shear stress. Your horizontal axis is representative of your normal stress. The 2 ends of your circle on the horizontal plane, your sigma 3 and your sigma 1 value, are your minor and major principal stresses, and they are the points or the orientations at which the shear stress is 0. And then your radius here is representative of when your shear stress is at the maximum value, right? And then your middle point here is just your average normal stress. Okay, and the whole point of Mohr circle is that you don't have to use your stress transformation equations, which were the really big equations that I showed you guys in the beginning of this crash course. You don't have to use those. All you have to remember is that the entire Moore circle that you've drawn there is representative of all the infinite number of orientations that you can rotate the soil particle. And so, like, visually you can see at every point on this circle, the normal stress and the shear stress is going to be different. But that's all there really is to Moore circle. Obviously the questions will get a little bit more complicated, but I would just highly recommend remembering those more important components, because if you just remember those and you keep practicing, it'll become second nature and you'll be able to really easily work through the more complicated ones. Okay. The workshop questions in soil mechanics are really, really quite helpful. So if I could give any advice, it would be to definitely work through those and make sure you understand all of them. But for now, I'll just move on quickly to the next topic, which is looking at the stress in a soil sample at a certain depth. So as you can imagine, if you imagine like the surface of the ground and then you're taking various points underneath the ground in the soil, the stress applied to each of those points is going to change depending on a bunch of different factors, one of them being depth, another being the surcharge, which is the type of load that you've got on top of the surface, if any at all. And all of those factors will play a part in determining the stress value at a certain point in the sample. So let's just look at a little bit of theory. Let's just go back. Look at a little bit of theory. Okay, so one of the more easier concepts in this topic is looking at one-dimensional loading. So that is when your change in normal stress is equal to the surcharge, right? And then 3D loading is when you've got like a loaded area that is less than or like equal to the soil layer. But for now, let's just look at one-dimensional loading. So that's if the dimensions of the loading area are a lot greater than the soil thickness. So here I've got like a diagram, and you've got your soil point here that you're studying, the elevation, which is going to be your Z value in most cases, and then here, because it's one-dimensional loading, your change in stress is equal to Q, right? But more often than not, the loading is going to be three-dimensional loading, where the width of the loaded area is going to be equal to or less than the soil layer thickness. And there are two methods in which you're going to be able to solve these problems. One of them is one of them is the 2-to-1 method, and then the other one is the theory of elasticity. So let's very quickly look at this diagram here. This is quite important. I would highly suggest just like memorizing the different notations, because you're going to see them in your questions a lot. So if you imagine the surface of the ground being up here, your Q is going to be equal to the surcharge per unit area. Your B is going to be your breadth. Your L is going to be your length. And it's kind of like the deeper you go, or the greater your Z value, the greater your B and your L become, as represented in this formula here. So as you can see, the deeper that the soil particle is, the greater that this value is going to be, and this one. And when you sub them into this formula here, the change in stress is going to increase. Okay, let's go up to this part here. The reason why it's called 2-to-1 method is just because of the way that the stress increases like linearly as you get deeper and deeper. But that's, there's a certain way that it's derived, and I can't really explain it, but it's definitely going to be in your lectures. So if you're interested in that, I would look at those lecture slides. The shape of your loading also matters as well. So you could have like a uniformly loaded rectangle or a uniformly loaded circle, at which point you're going to have to change the way that you account for the different types of dimensions. So here, for example, is the uniformly loaded circle formula, where you take into account not the breadth but the radius of the circle. And that's what the formula becomes to represent the change in stress according to your Z value. The other thing that you'll have to consider is that you'll have to use some figures. So depending on the type of load that you have, this is for the uniformly loaded circle, you'll have to be able to read these figures. So on this axis, you've got the depth over the radius, so that ratio. And then here you've got the I value, which is the stress in percentage of the surface contact pressure. So in your lectures, they'll teach you how to read that graph, and you'll just have to use those values and sub them into this formula here. It's a lot easier when you've got a rectangle, because it's very similar to the formula that I showed you down there, which is just the stress increases according to the total load over the total area. Sometimes you've got things like strip footings, which is still a uniformly loaded rectangle, except the strip footing basically considers that the entire length is like really long, and so it just simplifies into this formula here. But yeah, that's kind of the different ways that the type of load can determine how you're going to need to calculate the change in stress. I'll show you an example. Here we go. So here's an example from one of the lectures, where this is a very common diagram. So it's just a plane view of the surface of the soil sample. So you can see that the depth of the soil sample from the surface, I'll just read through the question. So it's asking you to calculate the increase or the change in the vertical stress at a depth of 2 meters below the point, which is O, due to the rectangular loading shown in the opposite figure. So they've basically taken this diagram, and according to the origin point, they've split it into 4 sections. So this is using the Busenik's method. One thing to consider is that when you use this method here, you have to use Fadam's chart, which you might have seen in your lecture slides already. But the whole idea is that you take each section and you calculate the stress on the soil in each section, and then you combine them at the end. So let me go down to this part. Once you figure out the I value, which I mentioned before was the stress in percentage of the surface contact pressure, once you calculate the I value for each of those sections there, using Fadam's chart and the breadth and the length values, you'll be able to sub each one of those values into the formula here for the change in stress, and that will just give you the overall delta sigma here, which is 78.1 kPa. I went through that quite fast, but that method isn't too bad, because you just take the diagram that they've given you, you split your sections accordingly, and then all of the answers should be on the Fadam's chart here. So as long as you learn how to read that well, you'll be fine with that question there. The more important one to remember is the 2-to-1 method, which were the formulas that I was just showing you before. So again, this is kind of an example diagram where you've got the surface load here, and the stress is going to keep increasing the deeper you go. So in this particular question, you're looking at soil that is 2 meters below the surface. And so because the depth is 2 meters, that's affected the breadth value and the length value that you use. So you can see here we've done the B plus Z times L plus Z. The 100 there, if you go back to the formula that we were looking at before, is your surcharge value. And then again, the B times L, that's your original breadth and your original length. So it's kind of like taking all of your values from the original surface and then dividing them by the new breadth and the new length, or like the new dimensions that have changed according to the Z value, which in this case is 2 meters. And then after that, they got a value of 51 kPa. Okay. This is kind of like a combined example where they've used both the 2-to-1 method and the Fadam's chart method. So they might ask you to do different methods as well. I would get really familiar with drawing diagrams like this because they become quite helpful. In this example here, it's kind of interesting. They've taken, or they've asked you to calculate the change in stress, not according to the depth, but according to the change in surcharge. So you'll see in this diagram here, there's no load. And then they've added a surcharge of 250 kPa. And so they're asking you to calculate the change in stress on the soil particles once the load has been added. But those are kind of the basic concepts in the stress topic. Let's see if we can go through a workshop question. Okay, it's week 3. Let's look at this one. Oh no, actually let's look at this one. Okay. So the soil profile, which I guess Millie would have shown you a bunch of different soil profiles and like different soil types as well. So hopefully you remember some of these terms there. The soil profile at a level site, which means there's no change in elevation between the layers, consists of the following values here. So in this question, I really like that they've given you a very clean overview of the dimensions of each layer. It just makes it very easy for you to visualize. So as soon as you see information like this, the first thing that you should do is draw a diagram, which is what has happened here. So start by drawing your soil profile. So put in all of your dimensions. You know that the length or the depth of the sand gravel is going to be 0 to 4 meters, and then from 4 to 10, which is 6 meters, is going to be dense sand. And then label your unit weights accordingly and your K constants. The other bit of information that they've put in is that the water table is well below the soil surface. So when you see things like that, what they won't do in the soil mechanics questions more often than not is that they will just say things like this. So well below the soil surface, and you just have to remember that that means that the water table is not going to be considered. So the soil is dry, right? And they're asking you to determine the horizontal stress at 2 different points. One that is 3 meters below the surface, which I've labeled here as A, and one that is 5 meters below the ground surface, which I've labeled as B, right? So just start, do 1 point at a time. Keep in mind that they've only asked for the horizontal stress, so it kind of means that you have to do both, just because you can't work out the horizontal stress without doing the vertical one. So don't get caught out by that. But for the first part, you don't have to do too much. You just have to use these formulas here, which are going to be on your lecture slides. They're taken right from the notes there. Sigma V is just representative of your vertical stress. Z is your elevation, which in this case is 3 meters. Oops, yeah, 3 meters. And then because your dimension has not exceeded the second layer, you know that your unit weight is just going to be 18, right, which is the sandy gravel unit weight. So you multiply those and you get a vertical stress of 54 kPa, after which you can then use that value to solve for your horizontal stress, which you've been given all of the values in your question. You know that point B is has exceeded the layer and now is in the second soil type, so it's the dense sand soil type, which means that sorry, I'm getting a bit ahead of myself. We still haven't calculated the horizontal stress at point A. So you use this value to calculate the stress here. My bad. So 0.3 is the K value they gave for the first sandy gravel type, and then you multiply that by your change or your vertical stress value here. Okay. Next, you can finally move on to the second layer. So again, you're using the same formulas, except you have to consider that the soil in the second layer is going to be affected by whatever is in the first layer. So that's why you had to calculate all this first. So you'll notice that in this point here, you're doing the same thing, except you're doing the sandy gravel soil plus the dense sand soil. Okay. So yep, you've got the 4 meters there multiplied by the unit weight of just the sandy gravel, and then you've taken the values for the dense sand. Make sure that you don't get caught out by the different measurements. So point B is 5 meters below the surface, which means that you're taking the entirety of the sandy gravel layer, but you're only taking 1 meter of the dense sand layer. So you don't need to worry about anything below that point, which means that this value here, or your Z value, is just going to be 1, right? Because you've already taken into account everything else above it, right? So you just get a value of 89 kPa there, which you then sub into this formula here to get your horizontal stress. Okay. Okay, so now we've talked a little bit about Mohr circle, which was about the stress on a certain soil particle and how it changes when you orientate that specific particle in an infinite number of ways. We also talked about stress at a certain depth and how the amount of stress applied to a specific particle will change according to the Z value, which is like your elevation. And finally, I'm going to talk a little bit about one-dimensional seepage. So everything that we've done up until now has not considered that when you're dealing with a certain soil sample, there might be a volume of water flowing through a passageway. So when you're considering a sample of soil, you would have learned in like week 1 and in Millie's part of the crash course that a soil is going to have void space, which is made up of air and sometimes water. And when you have void space, the water is allowed to flow through that specific space, which can change the way stress is calculated. So I'll just point out this diagram here, which is quite important. The sigma-V formula is representative of something called effective stress. And effective stress is a really important parameter when calculating stress in soil, because basically what it is that it's all the stress applied to a specific point in the soil, disregarding the pore water pressure. So as you can see here, you've got your vertical stress there, which can be calculated from using this formula here that we talked about before. Whoops, where is it? Let me find it. Oh, here. This formula here, you use to find the total vertical stress. And then once you minus the pore water pressure using this formula there, you're able to get the effective vertical stress. And it's important to realize that this formula is only true when the flow is equal to 0, right? Once there's flow included, the calculations kind of change. Okay, so let's just have a look at some theory here very quickly. There are some really important concepts and terms that will be thrown around in the week 4 lecture. I think it's the second lecture of that week. So this diagram here is kind of pointing out the differences in pore pressure at different points, so point A, B, and C. You can kind of see here that since the water is being pumped out, that there is flow. And so the points at the soil boundary, which you can see are like here and here. When you're drawing a diagram, make sure to label the soil boundaries really carefully, just because they're really important points in the diagram. They're not affected by the flow. Another term is the piezometers, so they're a way to like measure pressure according to the depth. And they cancel the limit out, and they'll always show the actual pore water pressure value, which is the gamma W times the height of the water, which is your ZC value here, which I've written in white on the diagram. Okay, so some factors that affect the flow are the change in head, which I'll define in a moment. The length of the soil passage, that will determine how quickly the flow is moving through the soil passageway. And also the void space, so how much empty space there is between the soil particles for the water to actually flow through it. Okay. One specific part, or one really important notation that you'll have to remember is the rate of flow, which I'm sure you guys have heard about in fluid mechanics and everything. I won't spend too long going over it, but that's a really important part of calculating stress or taking flow into account when calculating stress. Head relates the energy in the water to the height of an equivalent static water column. So that's kind of what is happening in this diagram here. So the change in head between point A and point B affects the rate of flow throughout the soil passageway or whatever you're examining. Pressure head is related to the height of water above the point of interest. So again, let's look at this diagram here. The height of water above the point of interest, let's say it's C, would be equal to ZC. And that would give you your little HP value, which will often be equal to the pore water pressure divided by the gamma W. And then finally, the elevation head is equal to the height of the point of interest. Let's say that that's A here, above the datum, which in this case is down there. Often you'll have to choose your own datum, so pick something that's easy to work with, but yeah, that's the difference between point A and the datum chosen here. And all in all, I know that was quite a lot of information thrown at you, but the more important concept to kind of wrap it all up is, I guess, written here, which is the total head calculation. So all you need to remember is that the total head, which is your height, like your height value related to the pressure value, is equal to the elevation head plus the pressure head. So as you can see, it's kind of demonstrated here. Your elevation head is from the datum to the point of interest, going from the very, very bottom to the point that you're studying, which in this case is point A. And then from point A up to the height of the water table, there should be a little like triangle there to demonstrate that that's where the water table ends. But this point here, HP, is your pressure head. And when you add them all up, you'll get your big H, your delta big H. So from this point here to there should be a label there to say that it's the total change in head. Okay. Yep, I've just kind of written that here again as well. Here's a better diagram, I guess. So I've labeled the datum there and kind of labeled the pressure head here, which is from, oh, sorry, the elevation head, my bad, from the datum to the point of interest, and then again the pressure head above that. You can see here that HW is also a way to notate the pressure head, so don't get confused between those two. Similar with HE, it can also be labeled as Z, and in which case your total H is also equal to Z plus U over gamma W. Okay, that's kind of all I really wanted to cover in terms of 1D seepage. Those are the main points that you're going to use in your workshop questions. I don't know if I have any 1D seepage questions to go through in these notes, but they should be on the Google Drive link. But yeah, that's kind of all I had to explain about week 3 and week 4 of the soils topic. So hopefully you understood that, and thank you for sticking around.